All right, let's talk about characteristic X-rays now. So characteristic X-rays are significant because we use them to produce what we call monochromatic X-ray radiation. All right, so what we mean by monochromatic is, mono means one, and chromatic is referring to color. So basically, we're talking about a single wavelength. So these characteristic X-rays that you saw in the previous sketch are what we use to produce this monochromatic X-ray, and this is useful for most diffraction studies. So that's what we're going to use. So now we want to sort of understand what's happening that produces these characteristic X-rays. All right, so let's imagine that we have, a source of electrons like we saw in the X-ray tube, and we have they're sufficiently high electrons, and then we want to look at a single atom. So we have, and I'm just going to obviously draw a very simplistic sketch of an atom, right? So we have the nucleus, and then we have the electron shells, right? So we have the K shell, L shell, and M shell, right? So this is just a simple schematic, obviously, but imagine that we have electrons coming in, and then we want to see how those electrons interact with an atom. All right. So what happens is that these high energy electrons have sufficient energy to excite an electron in the inner shell. Right, so a shell, basically an electron in the K shell, or something in the L shell. So let's start with one of the electrons here. So let's say that my incoming high incident electrons from my tube have enough energy to excite this K electron. So that is going to some other higher energy state. So maybe it's going to the L or M, right? Basically, that energy here is transferred to the electron, and it can jump into one of the higher energy shells. All right, so that's the first step. So inner shell electron goes into a higher shell. So what happens, so let's say it goes up here. So what happens is it leaves behind a vacancy, right? So in that inner shell, it leaves behind a vacancy. So that vacancy is kind of unstable in this atom. And so an electron that's from one of the higher states, an L or an M electron, let's say it's this one right up here, then that's going to come down and fill the vacancy. Fills the vacancy. And it does this because this is at a lower energy state, right? So it would much rather be in this lower energy state. So the process of doing this, so if you think about this, for example, this electron in the M shell has fairly high energy, And if it goes into the K shell, we know that energy is proportional to the the quantum number. So the number is lower in the K shell, n equal 1, and so the energy is lower, right? So it goes from a higher energy to a lower energy state, and so because we have conservation of energy, the difference in energy is what gives us the X-ray. So basically that energy difference results in this X-ray, right? So X-ray is generated by the change in energy from higher to inner shell electron. Right. And we know that energy is quantized, right? That's what the quantum numbers tell us. So we have a discrete value of energy at the level up here and a discrete value down here. So this energy in the form of an X-ray that is sort of liberated or generated is a specific energy. So this X-ray has very specific energy, and that translates to having a specific wavelength, because energy and wavelength are very much related in radiation. Okay? So this is what gives us this characteristic X-ray. And we call it characteristic because it's characteristics of these given transitions. So there's a specific energy, specific characteristic X-ray from going from this energy state to this energy state in this schematic. And so there can be multiple different types of characteristic X-rays. But for the one I've drawn, that's what we would be looking at. All right, so let me sort of go back and sort of draw this a little bit larger. So I'm going back to the sketch I drew earlier. This is the nucleus, K, L, and M. So different transitions give us different characteristic X-rays. So when we have a transition from L to K, we get what's called a K alpha. When we have a transition from M to K, this is our K beta. So we have a K and then a sub, and it's the Greek letters alpha or beta. So so these are typical characteristic X-rays that you'll see. And so a couple other things to mention here. When we're talking about these, the probability of an electron from the L shell filling that vacancy that we talked about in the K shell is higher. So the probability is higher of this L to K than it is for the M to K shell. So basically the probability here is higher than the probability here. So what that means is that when we see this, the intensity, so if we have a white continuous spectrum of X-ray radiation, the intensity of the K alpha intensity of K alpha is about 5 times higher than the K beta. So that just comes from the probability, because effectively this is closer transition, so it's more likely to occur. So it's very well known that the K alpha will be higher in intensity than the K beta, and so that can often help us determine the K alpha, K beta. Okay, so I haven't really sort of told you that much about why we call them K alpha, K beta, just that that's what these are called, right? So with the first question on the quiz, what I want you to do is I want you to take a look at these names that we're talking about, so K alpha, K beta, and why do you think they're called that? So why do you think that's what we call the M to the L, or sorry, the M to the K and the L to the K? Why do you think they're called that? And see if you can extend it to what would we call something from the M down to the L. So what would this be called? So see if you can come up with that. And then when you're finished with that question, come back and we'll keep talking about characteristic X-rays. All right, so let's get back to the naming here and what would we call the M to the L. So this transition is known as the L alpha. So if we see something with this transition, or sorry, something with this transition that produces an X-ray, this is going to be an L alpha X-ray. So the way we do this, so we have a capital letter and a subscript Greek letter, right? So this refers to the final state, right? So it's going from an M to an L. So this final state here is what we have this. So you just saw it with these other two, both of those, the final state where the electron is going is the K shell. So those were both K alpha, K beta. So the second part of this, the subscript, so the subscript here actually refers to the intensity. So you saw here that the intensity of the alpha was 5 times more than the beta. So you might think that it's kind of to do with the step size, right? So this is n equal 1, n equal 2, so the step size is 1, so we get alpha, step size 2 is beta, but it's actually more to do with the intensity. And those two kind of go together, but this is to do with the intensity. So alpha is the most intense, and then if you had another one beta, another one gamma, and so forth. So that's what this second is referring to. All right, so let's look a little bit closer. We saw this K alpha. So there actually is a little bit more going on with this K alpha than we might suspect from this drawing here. So let me draw you another version of this. So we've got the K shell, and then in the L shell, we've actually got 3 subshells in the L. And they're very close in energy. So we can have a transition from L2 to K, and we can also have a transition from L3 to K. This one, so they're both K alpha, but this one we call it K alpha 1, this one we call K alpha 2. And so, you know, they're very close in energy, so I've kind of exaggerated it here. But if you want to sort of get an idea of the various wavelengths, if we look at the wavelength of K alpha 1, this has a value of 0.15406 nanometers. If we look at K alpha 2, this has a wavelength of 0.15444. So you can see that they're really close, right? So there's not that much difference. In comparison, if you want to see beta, K alpha beta, or sorry, the wavelength lambda and then K beta, this has a value of 0.13922. So much different than how similar these two are. So it's so just this is something to kind of keep an eye on, because we often think of K alpha as a singular wavelength, but in actuality, it has two components. They just are very, very close together. And so oftentimes you can't even tell that those two are separate. Oh, and I should mention, I didn't mention this here, these are all for copper. So these are all wavelengths of copper. So this is our copper target. And so the different transitions are for electrons hitting the copper and producing these different transitions in copper. So I just wanted to highlight that.